Download this code from codegive.com, link in the description below. Don't make these mistakes. The right way to use seeds, with code examples. In the realm of programming, particularly when dealing with random number generation, simulations, and algorithms reliant on stochastic processes, the concept of seeds is crucial. Seeds provide a way to control and reproduce seemingly random behavior. However, improper use of seeds can lead to misleading results, hinder reproducibility, and introduce subtle bugs that are difficult to track down. This comprehensive tutorial will delve into common mistakes made when using seeds, illustrate the correct approaches, and provide code examples in Python to solidify your understanding. What are seeds and why are they important? At their core, pseudo-random number generators, prngs, which are what most programming languages use to generate random numbers, are deterministic algorithms. This means that given the same starting point, they will always produce the same sequence of numbers. That starting point is the seed. Importance of seeds reproducibility seeds allow you to rerun experiments and simulations with the exact same random numbers, ensuring you get the same results. This is critical for debugging, verification, and sharing your work with others. Controlled experiments in scientific research and machine learning, seeds enable you to isolate the effect of different variables by keeping the randomness constant across different runs. Testing seeds are invaluable for writing repeatable unit tests for code that uses randomness. You can ensure that your code behaves as expected given a specific set of random inputs. 2. Common mistakes with seeds, and how to avoid them. 1 mistake, relying on default seeding, or no seeding at all. The problem when you don't explicitly set a seed, most prngs will automatically initialize themselves based on the current system time or some other unpredictable factor. This means that every time you run your code, you'll get a different sequence of random numbers. Why this is bad? This makes it impossible to reproduce your results. Imagine you are training a machine learning model, and each run produces a slightly different model. It becomes difficult to compare performance, debug issues, or share your findings. The solution always explicitly set a seed when you need reproducibility. Choose a fixed integer value that is meaningful to you or documented clearly in your code, example a seed for a particular experiment or a standard seed for testing. Code example, Python. 2 mistake, using the same seed for independent processes. The problem if you need multiple independent streams of random numbers, using the same seed for each will cause them to produce the same sequence, which is likely not what you want. This defeats the purpose of randomness. Why this is bad? This introduces correlation where you expect independence, leading to biased results and inaccurate simulations. Consider a simulation of 2 independent agents. If they both use the same random numbers, their behavior will be artificially synchronized. The solution generate different seeds for each independent process, either by incrementing a base seed, using a function to derive seeds, or using a dedicated stream splitting mechanism, available in some libraries, like NumPy's generator. Code example, Python. Explanation of NumPy's generator and streams np.random.default_rng, seed, creates a generator object. The generator is the recommended way to generate random numbers in NumPy, replacing the old random state object. It offers better statistical properties and more flexibility. Range spawn, key, creates a new, independent generator object derived from the original RNG. The key is an integer that acts like a subkey for the new stream. This method efficiently generates statistically independent streams of random numbers. The numbers produced by the spawn streams are unrelated to the numbers produced by the parent stream. This is much better than simply incrementing seeds, as it uses more advanced techniques to guarantee independence. 3. Mistake, not documenting your seed values. The problem you use seeds for reproducibility, but you don't document which seeds you used, why you chose those seeds, or where you set them in your code. Why this is bad. Future you, or someone else, will be unable to reproduce your results without a significant amount of detective work. This negates the whole purpose of using seeds in the first place. The solution. Meticulously document your seed values. Include them in your code comments, experiment logs, or configuration files. Explain the reasoning behind your choice of seed values, especially if they are related to specific experiments or scenarios. Code example, Python, with good documentation. 4. Mistake, confusing reproducibility with true randomness. The problem. You believe that because your code is reproducible due to seeding, it's generating truly random numbers. Why this is bad. PRNGs are not truly random. They are deterministic algorithms that produce sequences that appear random. If you need true randomness, example for cryptographic applications, you should use a source of entropy from the operating system, like /dev/urandom on Linux, or a hardware random number generator. The solution. Understand the limitations of PRNGs. They are suitable for simulations, games, and other applications where statistical randomness is sufficient. However, if you require cryptographic-grade randomness, use a dedicated entropy source. Code example, Python, using secrets module for cryptographically secure randomness. 5. Mistake, seeding at the wrong granularity. The problem. You set a seed once at the beginning of your program, but then run multiple independent sections of code, each requiring its own reproducible randomness. Why this is bad. You might inadvertently affect the randomness in one section of code from the randomness used in another, even if they are logically independent. The solution. Think carefully about the scope of your randomness. If you have distinct sections of code that need independent random behavior, seed each section separately, using different seeds, as explained earlier. Code example, Python. 3. Best practices for using seeds. Always set a seed when reproducibility is needed. Use descriptive seed names, example model_training_seed, simulation_run_1_seed. Document your seed values and their purpose. Use different seeds for independent processes or streams of randomness. Employ techniques like incrementing seeds or using number_generator.spawn, for better independence. Be aware of the scope of your randomness seed at the appropriate level of granularity. Understand the limitations of PRNGs. Use dedicated entropy sources when true randomness is required. Test your code with different seeds. This helps ensure that your code is robust and not overly sensitive to the specific sequence of random numbers. Consider using a configuration management system, example YAML, JSON, to store and manage seed values. This allows you to easily change and track different configurations. When using libraries like PyTorch or TensorFlow, remember to seed their random number generators as well. These libraries often have their own separate PRNGs. 4. Advanced techniques. Seed derivation functions. Instead of simply incrementing seeds, you can use a hash function or other deterministic algorithm to derive a series of seeds from a single master seed. This can help ensure that the derived seeds are statistically independent. Asterisk statistical tests. Asterisk if you are relying heavily on randomness, consider performing statistical tests on your generated numbers to verify that they meet your requirements for uniformity, independence, and other properties. Conclusion. Asterisk. Properly using seeds is essential for creating reproducible, reliable, and understandable code that relies on randomness. By understanding the common pitfalls and implementing the best practices outlined in this tutorial, you can avoid introducing subtle bugs and ensure that your results are trustworthy and replaceable. Remember to document your seeds meticulously, and always think carefully about the scope and independence of your random number generation. Using NumPy's generator and stream features is highly recommended for robust and well-designed random number management within NumPy-based applications. Good luck.